I don't see the cable to connect to my laptop. So I logged in from this computer just to share the syllabus. No. So it's solar. Do you know how I can go to solar from this page, or I can just Google solar?
On Google Solar and Sun Group.
Oh, it's here.
On Solar login.
Yeah. Now for some pages they ask your name, for some your ID. Okay. So it's my ID. Oh, wait a second. I should go to bright space. It's bright. It's not the solar. Bright.
Oh, Professor, ask for the username, not the member.
Oh, I should use the username?
Yes, yes.
Oh, that's what I think. Sometimes, yeah. Here. Okay, yeah, it worked. So this only to project um, the serials. Okay. So, okay, let's get started. I want to start with this announcement. Uh, do you have the access now to the course shell on Brightspace? Can you see the announcement? And
No,
oh, you can't access it.
yeah, my Brightspace said that there are no courses to show, which is
Okay.
yeah,
Okay.
I don't think it's an issue with your side because I enrolled
I see.
into other classes as well.
Uh-huh. Well, yeah. So for now, it's completely fine. So just few announcements that um I will have a conference next week. So next Monday class will be shifted on Zoom, and next Wednesday class will be canceled. Um, Instead of Wednesday class, we will have class during midterm, and midterm will be take home. So we will use the time from midterm for the class, and midterm will be take home. So these are a few announcements. Um, Now let's look at the syllabus. Um, um, so maybe it's easier. So if you go to for course first module, I uploaded the literature. So if you took machine learning class earlier, I believe you should know this first book by Bishop, Pattern Recognition Hello. What's well, I will ask you later about your background. So, Bishop Pattern Recognition is a like classical machine learning textbook, which also covers probabilistic models there. Um, a couple of years ago, he published with his son another textbook on deep learning, where they covered diffusion models. But also, I have my notes in progress, and maybe it's easier to grasp the course idea from the contents of my notes. So, um, let me just give you a quick overview. Um, so the first part is Bayesian models before deep learning, before neural networks, and usually they cover um, Bayesian linear regression, Bayesian logistic regression, latent variable models, which covers principal component, probabilistic principal component analysis, probabilistic mixture of Gaussians. Because if you don't know the distribution of your data, you always can put a Gaussian at each data point with very narrow variance and consider your distribution as the mixture of these Gaussians. In other words, you can approximate and there is a theorem, an arbitrary distribution with a mixture of Gaussians. So that's why mixture of Gaussian models is mixture of Gaussians is an important model. Uh, and then if you want to sample from distributions, then there are different sampling methods like Markov chain, Monte Carlo. I'm not sure if we will talk about Gaussian processes and non-parametric Bayesian models. But after that, the deep learning, like Bayesian neural networks, come into play. So this is kind of the second part. And this is more recent, I believe. It began to develop from variational autoencoder, and it was published in 2014. So this is approximately when Bayesian deep learning starts. And first, we should understand how we can actually use the probabilistic models with neural networks with the gradient descent. So it's stochastic inference. And then the models, we will start the models, variational autoencoder, normalized flows, which are like more popular, but maybe 2 years ago, but nowadays they were replaced by diffusion models. Gumbel softmax is the trick to work with discrete distribution instead of continuous distribution. And then diffusion models, which are still everywhere in like text to image or text to audio production. And a more recent topic, which wasn't covered by Bishop book because it emerged just approximately in 2020, optimal transport. So optimal transport helps to speed up diffusion models because if we talk about I will start from the end. If we talk about diffusion models, we kind of transform a simple distribution like uniform, like standard Gaussian. In this case, it transforms distribution into mixture of Gaussians, into more complex distribution. But you can see that the trajectories are noisy. They are stochastic. If we consider, let's see, if we consider, so another approach is called flow matching. So we connect points from both distributions by arbitrary straight lines. And then we learn so-called velocity field. So you can see the trajectories now are smooth. And it means that they can be described by differential equation, like x derivative with respect to time equals to velocity. And if our neural network learns this velocity, we can integrate and find the x at, for example, if we start at time 0, and our endpoint at time 1, we can calculate integrate of this velocity from 0 to 1, and we will end up at the target distribution point. It works faster than integrating the stochastic paths. So this idea came from optimal transport, because in optimal transport, what is the shortest distance? It's just a straight line. So this idea came from optimal transport. Of course, when we measure them arbitrary, it's not optimal, because you can see these lines can intersect, so it's not the shortest path. But after learning the correct velocity field, you can see that trajectories are not intersecting anymore. And ideally, we should connect them with the straight lines. In that case, it will be optimal transports, like pure optimal transports, not the approximation. But I just wanted to explain you why optimal transport is also in this course, because it's kind of the modern generalization of probability transformation from one distribution to another distribution in different ways, like noisy paths, smooth paths, and straight paths. Okay, so this is about the general topics. Now I want to hear what. Well, maybe I will say one more thing. Did you hear about stable diffusion models like text to image, or Sora 3, or what else? DALI model, more like previous text to image model. So they all work using diffusion models or these smooth trajectories. Now they all, of course, moved in flow matching because it works faster. It's the same idea, but originally they used stochastic path diffusion model. Oh, by the way, there is another reason why we want to use diffusion instead of smooth paths. Because with diffusion, with stochastic paths, with stochastic trajectories, well, this model is called Schrödinger bridge, but the idea is the same. With stochastic trajectory, you don't know at which point you will end up because it's noisy. But if you use differential equation, you always end up in the same point because it's a deterministic system. So sometimes if you want to generate every time slightly different objects, you don't want to use flow matching, so you want to use diffusion because it allows you to generate different samples from the same noise sample. So yeah.
So the flow matching model is not a probabilistic model?
No, because yes, flow matching is completely, so okay, you can see there are some equations. So W stands for Wiener process. So if you remove that, it will be flow matching. So it doesn't contain noise. Yes. And then it's just normal differential equation. And as the result, well, there are some details that we will go into in this course, like you use theta neural network parameters, and you want to approximate the velocity field, and you solve this non-stochastic deterministic differential equation with initial data at one point, and when you integrate, you end up with, you can transform this, let's say you have just Gaussian distribution, multidimensional, and you transform this into image of cat, for example. It has the same shape, like 32 by 32 image, for example, but with time, the distribution is changing from noise to the image distribution. So this is the general idea. And you can change it in deterministic way or in stochastic way. And the main problem is to learn to approximate this velocity field, which is you could hear score-based models, so which is score or gradient of the logarithm of the probability density. So, but this is kind of the underlying math, but what is the structure of neural networks? Of course, nowadays it's transformer models. So I don't know how much do you know about neural networks? Did you work with PyTorch with?
It's like in some like cross project.
Okay, so like multi-layer perceptron or feedforward neural network, you know. What about you guys?
Oh, I have been working on the activity in live detection. So
Okay.
the algorithm I'm using right now is a transformer. So I
Okay.
use the transformer to get the radio frequency data, and using the radio frequency data to predict what kind of activity the people is doing.
Okay. Oh, is it voice activity or
it's
just
It's like walking, sleeping, brushing teeth, washing your face, that kind of activity.
so it's visual?
Oh, no, it's
Oh.
not visual, it's from the radio frequency data. So we are using the ultra wideband data. It's like Wi-Fi, it's in signal. You're shooting a signal from a sensor, and when the signal reaching a participant or a human being, will be bounced by, and the frequency will change. So we see the change of the frequency, and also we see the strength of the frequency, so we can know what kind of activity that participant is.
Yeah. So you work in frequency domain? Hello. I mean,
It's not the frequency domain, we have a heat map. Heat map sets, specifically the x-axis, it's the range, which means how far away that participant is away from the sensor. And the x-axis is the velocity, which means how fast the participant is moving. So we use these two inputs to predict, because it's a heat map. You can imagine if the heat map one point is being light up, which means I know the participant is X meter away from the sensor and moving with the Y velocity. So using that information, I can know what kind of activity that participant is doing.
so your input is like by
Image. Yeah,
like image?
yeah, like image.
So you're using something like visual transformer or something
Oh, yeah, very similar, bit transform reactive.
Or there's also time.
Yeah, there's also time, so it's a time sequence B.
So it's more like video processing because there is image which changes with time.
Yes.
But what about you? Do you have experience with?
Oh, I actually from a very different department. I was from physics department, and I come here as an audience. And my background, I mean, I was trying to see whether I can use this machine learning method or to mimic the wave function that we typically study in the quantum system.
Well, actually, all these ideas came from physics.
Oh, really?
Yes.
Okay.
And
Like,
you could see
I saw a lot of
even
Schrödinger
Schrödinger bridge.
bridge.
Yes, it's actually the uh, drop that Schrödinger wrote in 1930s on turbulence. On turbulence.
Okay.
And turbulence.
That's a soft question even until now.
Yes, when your liquid or air
Passes
randomly, yes. So that's why this idea of yeah, you can think about probability distribution as the profile of the water in the river, for example. And if the I don't know, the shape of the river is changing, like there are rocks in the middle or something else, the profile of water is also changing.
That's true, yeah.
So this is the
It's
same
a diffusion
idea.
transition.
This is the same idea.
I see, okay.
Well, yeah, diffusion comes from gas because gas molecules in gas they are most stochastic. Than
Brownian
in liquid.
motions or something.
Yes, Brown motion, yes, is the or Wiener process, they are synonyms. So yeah, this came from physics. So and you came from physics to learn about physics from machine learning. Okay.
I mean, machine learning is quite useful currently in field of physics because actually there's a lot of undeterministic things like, for example, like wave functions in your quantum system. And a lot of people are trying to use this machine learning or architecture as an ansatz because you can actually use it to present or to simulate some targets wave function in the quantum system and to predict the property of your materials. That's the things that I wanted to learn. For example, like the basic architecture of your machine learning things or the wave or the neural network, and using that as representations for the system that I'm studying. For example, like the high temperature superconductor. How should I simulate that kind of stuff?
So yeah, like many topics, like Mark chain of the car was also
we were also using Markov
was also introduced in Atom projects 96s. Yeah, it's all coming from physics.
It's time to have some feedback. I mean, from this machine learning and to teach us or help us to solve the other problems.
Yeah, but I do everywhere underline ideas the if the minimizing of the energy.
That's true.
So we will also use these words like energy functional.
Yeah.
And
Minimize the energy.
and in machine learning we minimize it with gradient descent.
Yeah, there's a lot of similarities between
Yes. So what about you?
Actually, I'm doing some research on flow matching and
Oh, great. So you understand what I was talking about.
to avoid the hallucination or to bring the model, to avoid the model to generate some samples out of supply.
And what is the domain? Is it images? Is it audio? Is it language?
It's not limited on some
Or just general?
yeah, just high dimensional data.
it's hard to answer like all the head on this question, because as you could see, the fusion is so it has some uncertainty, and I look just by design, it may fall out of the model sometime. Flow matching is more constraints, less diverse. So the Schrödinger bridge model is also random process, but you can control the variance at the ending point. So, okay, but I think it will be anyways useful to learn these models for you. What about machine learning? The code with PyTorch or what?
So I'm very new in this field. I just got to learn to build a model about 1 month or 2 months ago.
Yes.
So I want to learn more by this class.
Yes. Sorry, I was asking about your experience with machine learning. Did you code with PyTorch before, or?
I teach a very little bit.
Okay. Do you know the transformer models? Because the main application of like the current computer models is the generation of images from text input, and this is what transformer does. So transforms like one domain to another. So I was thinking, so the course is mostly, I can read it as mostly theory, like how all underlying models and mathematics work, but we also can a little bit, how current generative models work. Then we will need transformers as the backbone of the scenarios. So, so for now, I want just maybe to restructure the syllabus and maybe spend less time on the machine learning before neural networks and spend more time on deep learning with current applications. So, what do you think?
Sounds good.
So, yes, I will. Oh, and by the way, in the beginning of the class, I mentioned that there is the syllabus. Oh, it's here. Yeah, so the literature is I uploaded to the first model module module and I just want to mention that next week on Monday will be class on Zoom because I'm traveling to a conference, and there is no class on Wednesday, and we will use midterm time for class, and midterm we will take home. And there is no final, there's final project. So it's not very heavy exam class. So Okay, let's go to maybe the first topic, and the first topic will be just reminding the probability and statistics. Making it off. Tap to turn on. Hold 3 seconds to turn on. What about the timing? Do you make breaks in between, like 40 minutes and 40 minutes of the class? No? Okay, we will see. Well, today's not it wasn't heavy first part, so we can go without break, but maybe we will do break in the future. And there were a few graduate students who asked me to record the class, couldn't join today. So I will also record. So let's, because we'll work with probabilistic models, I want to start with probability theory recovery and statistics. And let's think about a simple flipping of the coin. So you flip a coin, and you can have heads or tails, 2 outcomes. And in definition of probability, we usually talk about 3 objects. One is called the space of events, or probability space. Another one, or also it's called the space of elementary events. Another one is the combination of events. And it's called sigma algebra. Let's denote this. So sometimes it's denoted differently, but usually by calligraphic letters. Sometimes people call this field, and then instead of A, you can see letter F. But ideal field is like older school notation, because if we will talk about algebra of events like union, intersection, complement, negation, it doesn't actually satisfy the field axioms. It's an algebra, but maybe so maybe people then realize that, and in more recent books, usually it's called algebra of events. But because by algebra you can call anything, like if you have any operation, binary operation, addition or multiplication or union and so on, it's an algebra. But field requires satisfying specific axioms. And there's one axiom which union doesn't satisfy. It says, and the first element is the measure, or probability measure, or simply probability defined on the space of events. So this triple is called probability space. And now I will row every component in this notation. Probably. Space. So if we flip heads and a coin, what will be the space of events? Yes, it will be either head or tail. Now, what is the algebra of events? Simply by, well, when the space is discrete, we just take the set of all subsets. So, for example, if you think about a ball, it can be on or it can be off. So, like in a room, there is one bulb, and how many ways to illuminate our room with one bulb? Turn on. But how many ways? Huh? Actually, two, because either it's on or it's off. So now let's think about two bulbs. So the first case is simple, like either it's off or it's on. So two cases. Now, now let's think about two bulbs. How many ways to illuminate a room with 4? Yes. So can you derive this from one bulb? So if one bulb can be on or off, so let's use one bulb, and then we add a new bulb. A new bulb can be off, and new bulb can be on. So it means that the number of illumination with one bulb we multiplied by 2.
It's direct.
Huh?
It's a direct product of two things.
What is it?
Direct product.
The product? Yes. But I want to now to make one step further. And what if we have n bulbs? What if we add, for example, if I add the third bulb, how many ways we will have? 2 power 3, yes, because here we have 2, here we have 2 times 2. Then we will multiply this number of ways by 2, we will get 2 power 3. And if we have n bulbs, it will be 2 power n. So that's why. So this example was to explain the notation of the set of all subsets. Because you will see often the notation 2 power set. It means that it's a set of all subsets. So if you think about bulbs, like you have n bulbs, every subset either include one of these bulbs or doesn't include. It means that this bulb is on or off. And different combinations give you all possible subsets. Okay, so let's just write all possible subsets of our set heads and tails. And we should have 4 sets. So what will be these 4 sets? It will be heads, but now it will be not an element, it will be like a set of one element. Heads, it will be tails,
Oh,
it will be the whole omega, heads and tails, and empty set. Okay, so this is what is called sigma. So in probability, this is called the event space or elementary event space. And this is called, well, it's called sigma algebra if the number of events is infinite. If it's finite, then sigma algebra is the same. But I just give you general notations. Sigma algebra or sigma field, if we use all the notation of events. And this is the probability. So, okay, we define elementary events, we define the normal events or all possible combinations of these events. Now we should define the last element, probability. So probability is defined on A, not on omega. So we should define 4 numbers. What will be how, and this is up to us how to assign the probabilities to these 4 events. So just give me some ideas how we will assign probabilities. Okay, 1/2, 1/2, 0, 0, 0. So if we have this event, it means that we always will have 4 heads or tails. So it's better to assign 1. And here is 0. Let's see. There's no something. Wait a second, or maybe 0, because it means that we have heads and tails. Oh, maybe you're right. Yes, we should have. Yeah, because they should all sum up to 1. Let's see. No, I believe this should be 1 because let's see. That's my notes. No. Well, actually, I don't need to look at my notes because probability has three properties. And one of the properties is that probability of the event space is 1. So it should be 1. So sorry about this confusion. Because this event H and heads and tails is the same as union of these two events. And the probability of union of independent events is the sum of probabilities. So it should be sum of these numbers. So it's yeah. The sum of probabilities of this event space should sum up to 1. Great, we defined all three components. Now, let's think about another object, which is called random variable. Now we introduced random events, but we usually will work with random variables. So what is random variable? So by definition, random variable is just simply a function. I don't know which letters are used to use. So usually in statistics, people use capital letters. In probability, usually people use Greek letters like C, eta, and so on. So we will work mostly with statistics. So maybe that's why in machine learning you usually see capital Latin letters for random variables, but you should also be ready to see Greek letters because this is usually the probabilistic notation in probability theory. So if you don't know how to write C, it's the same as epsilon, and then you add the head and the tail. So a random variable is a function from the set of the set of all subsets or from the set of elementary events. Let's say it. I was hoping on my memory because those are like basic definitions. So random variable. Yes, it's a function from from elementary events. So it's a function from omega to real numbers. And how we define these numbers, it doesn't actually matter. So in case of a coin example, we can define a function which takes h heads, or we can use even omega lowercase and define as follows. Let's say it's 0 if omega is, I don't know, heads, for example, and 1 if omega is tails. But you could all use here also other numbers like 5 and 10 or just an arbitrary number. 0 and 1 is just the classical choice from any probability textbook. But the main step of which made Kolmogorov when he introduced, actually Kolmogorov introduced, he wrote his paper on diffusion processes a year before he published the axiomatics of probability theory. So it's interesting that he wrote a paper on Schrödinger's paper in 1931, but he wrote the book which is now cited as the first textbook with probability axiomatics in 1932. So he worked with random processes before he actually introduced axiomatics of probability. But why do we want this random function? Because we want to estimate some metrics like mean, variance, but we want to sum up, we want to integrate, but if we work only with events, what does it mean heads plus heads? It doesn't make much sense. So that's why Kolmogorov used this connection between real-world events and numbers. Because if we map our real-world events to numbers, we can then do all the math there, like with numbers and sum up and integrate and so on. This connection is done by this random variable, the function from events to real numbers. So now, how we will assign the probability for this function? This probability was defined on the event space. Now we want to define a probability for random variables. Like you remember, sometimes you see the probability that C is smaller than, let's say, 1. What does it mean? So for the beginning, I will use probability with subscript C to distinguish between probability on the space of events and probability on these functions. But later, and many textbooks do that, they omit this subscript. And then when at least I was reading, I always had confusion which probability they used. So what does it mean, this notation? This notation means that by definition, we should look at the probability of all pre-image of this function. So probability of all elements from event space such that our function of these events is smaller than 1. So this is just by definition. Okay, now let's compute. Let's look at the events for which Xi is smaller than 1. So we have just 2 events. Heads. If I use Xi of heads, it's 0. So heads fall into this space, into this set, because Xi of heads is smaller than 1. Now I will look at the tails, and Xi of tails is 1. It doesn't satisfy this inequality. So it means that I have just 1 event heads. Now I have the probability for events. Probability of heads is 1. And now if I use instead of 1x, how it's called, the probability of C smaller than x, it's called cumulative distribution function. So C D F, cumulative distribution function f of x is the probability with subscript C of C smaller than x. So this is just, again, by definition. And let's plot this function for our, well, you know that this variable, random variable, is called Bernoulli random variable. Well, actually, for Bernoulli, we use probability p and 1 minus p. So how to plot this function? So now, this function is a function of one variable x. If x is 0, let's calculate probability when Xi of omega is smaller than 0. Which elements will satisfy this condition? Xi of omega is smaller than 0. Only which element will satisfy? Only empty set. Only empty set. So, and the probability of empty set is 0. It means that this function, when x is 0 or smaller, will be always 0. Even for 0. Now, what will be for any number in between 0 and 1? So if we take any number in between 0 and 1, 1/2, yes, because only heads will satisfy the condition that Xi of heads is smaller than this number. And tails, they equal or greater than 1. So 1/2 so we don't include 0. And what will be for any number greater than 1? Let's say 2. if we look at the random variable or function c smaller than 2, then both events will satisfy this condition. It means that we will have both events and the probability is 1. So it will be 1 everywhere after 1. So this is the connection between real events, the heads and tails, like flipping coin, and CDF, the function which describes this process through a random variables. Yes.
Suppose we have 2 coins, what's going to happen? We should define some 2D CDF or still 1D?
Let's look at, that's a great example. Now let's look at 2 coins. I started from 1 just because it's easier to understand. Now let's, like with bolts, I started with 1, bolts with 2, and then with n. So now we'll do the same transition. Let's look at 2 coins, and then we will understand how to do for n coins.
Sure.
And after that, we actually will need to go to infinite number of coins, and then to continuous number of coins, if we want to talk about like time dependent stochastic processes. But yeah, we have 10 minutes. Let's now do the same, but in case of 2 coins. So now we have 4 events. The first coin ended up in heads, and the second coin ended up in heads. The first coin, the first flip resulted in heads, the second resulted in tails. The first resulted in tails, the second in heads, and the first in tails and the second in tails. Now we want to describe the what's called sigma algebra of events, or all subsets. What will be the size of this sigma algebra?
16?
16 to power of 4. Yes. So let's start from simple case, just 1 element events. So 1 element events will just repeat this form. So heads, tails. Oh, and I should use the set notation because it's a set containing only 1 element. Because it's the set of subsets. Tails, heads, and oh, so actually, this is an example of 2-dimensional space equivalent. And tails. So we have 4, and we still need 12 more. So next we will include 2 element events. So it will be heads and let's say heads, tails. So I will have four elements with heads on the first position. Then I will have, let's see, 3, I believe, elements, because one will be repeated. So then we will list all 2 elements events. Then we will list all 3 element events. And finally, we will include empty space and 4 elements event. And you should get 16 elements. And then we will need to assign probabilities. So oh, so well, the easiest way is assign 1/2 or 1/4 to 1/4, yes, to every element, and then you will get like standard probability, like probability of 2 heads will be 1/4, and so on. Now, let's take one step further and talk about statistics, and we will end like our probability and statistics overview with that example. Now, let's assume we don't know the probability of heads. Now, the goal is to infer this probability from our from experiment. I remember when in probability course, they told us that there's a law of large numbers, and it says that if you sum up the results of multiple events and take the average, it should converge to the mean. In other words, if you have an unbiased coin and you flip it, let's say 100 times, and divide by 100, you should get 1/2. So I flipped maybe 70 times, and the number was really close to 0.5. So, but now let's say we don't know if our probability of heads is 1/2. We just have the model. We just have a model that probability, let's see our random variable takes values 1 or 0 with probability p and 1 minus 2. So does it make sense, this notation, or so this is probability. Or in other words, I assign probability some number p to heads and 1 minus p tails. And the question is how to find p from several tossings. And this is the question of statistics. Any ideas? Did you hear about maximum likelihood principle? So, and in statistics, we usually use now capital letters X. And let's say we have n xn, and n goes from 1 to n capital. So we have now every tossing we represent by one random variable. With the same parameter p. If well, I hope you remember from probability, if our events are independent, then the probability is just the product of probabilities. So, for example, 1/4 was the product of 1/2 and 1/2. So we will use here exactly the same idea. The probability of the series of our events, x1, so on, xn, is the product of probabilities for individual event, and it will be x so x is 0 or 1. So it will be p if x equals, in other words, how many times we had heads. Let's use m, where m is the number of heads, times 1 minus p n minus n. This will be the number of tails. And now we should find the maximum of this probability. And to find the maximum of this probability, we should take the derivative, find 0, assign to 0, and you will get m over n. So if you will maximize this function with respect to p, the answer will be p lowercase is 1n over n. And this idea is called maximum likelihood. Maximum likelihood. Because this function is called likelihood. In other words, how likely that parameter p at this value to get the maximal value for this probability of joint events. But now we should stop, and next time we will see how Bayesian formula, Bayesian approach will change this formula, which will allow us to use this formula even if n is 0. Because for now, this formula is better if the number of samples is large. But with Bayesian approach, we will get the formula if the number of tossing, if we even didn't toss the coin once. Okay, so that's it for today. And I hope today to go, next time to go to Bayesian linear regression. But first of all, finish this example with Bayesian point of view. And I will refactor the syllabus to make faster to deep learning. Okay.